Yes. Okay. So I want to tell you about how we think cold spots form, and we think they're involved with this like granular wave kind of thing going on the bottom here. So let me just tell you what I'm talking about. So if you were to look at a fresh crater on the moon in the visible spectrum, that's what you'd see maybe on the right. But if you look at that same crater and you zoom out and you look at it in infrared at nighttime, you'd see something like the left picture, and that blue splotch is a cold spot. Um, So cold spots are these low thermal inertia halos that surround young craters on the moon. So they are cold, that blue area, because the surface regolith there is looser than the background or the green regolith. So you get this sustained temperature difference at nighttime. And so you're going to see them all everywhere on the moon, across terrains, any young crater, and they're quite large. So the average halo radius, which is indicated by this dashed line, which is or circle, which is not to scale. But that's about 100 crater radii. So we're talking 20 or 100 kilometers from the source crater. So much further away than surface ejecta could be modifying the surface, or yeah. And so it's not really, so you only see this temperature difference, right? So it's not clear how they form. And if you take that temperature difference and you fit it to an exponential model of density versus depth, you can see the solid line or the background or the green regolith has a greater bulk density than the dash line or the cold spot surface regolith. But we're contained to the first 40 centimeters here. So it's a very near surface effect where we're kind of dilating or decompacting or fluffing up the surface regolith in that region. And so we don't know how this occurs. So in the Banfield paper where they were first characterized, they proposed maybe this laterally rolling ground transport or maybe gas from the impactor. But so what we've been working on is this like kind of granular wave like we saw on the title slide. So let me tell you how I think that dilation is happening at the surface. So we have these granular dynamic simulations where we have this long channel of particles and we initiate a wave in the channel. And so I'm artificially maintaining this wave across the channel. I'm dragging a velocity across the floor. And here particles are colored by their vertical displacement. So you don't see the leading wave front, which is about to hit the wall, but you see what happened in the collision is you had this, or in the wave front, you had this frictional collision with the particles. And so those closest to the surface where gravity is lowest can like loft up after experiencing this wave front. And so as we move towards filling our channels with these particles that look more like lunar regolith, so larger elastic modulus and smaller particle size, we get more dilation response. And so through all this work we did, we were able to do two things. So we came up with this, we can predict the force in that wavefront that a particle feels based on that velocity I'm driving across the floor. And then if we equate that force in the wavefront with the gravitational overburden on the grains, we can solve for that loft depth. So like the cold spot loft depth, I think I forgot to mention that term, is about 40 centimeters, right? So the area that the surface grains are being like fluffed up. And so yes. So great. We have a way to like kind of back out, what is this floor velocity corresponding to some depth of modification? But like I mentioned, I'm artificially driving this wave across the floor, right? So on the surface of the moon, what could be doing that? So the waves we were just looking at are kind of going through the regolith region in the top right. So 100 micron size grains on average, a bit less. And the cold spot extent is not to scale, but right in there in the surface. And so what we're going to look at now is this mega regolith region, right, which is this kind of larger range of larger size particles that starts abruptly below the regolith. And actually, in a like 10-meter thick sheet just below the regolith grains, if you look with ground penetrating radar, you can see that there's these meter scale boulders in this like continuous sheet there. So now what we're going to do is look at in this region, kind of similar how we did before, can energy propagate over large distances, because there's this property of wave propagation in granular systems that's a function of say, particle number. So what I mean is, if a grain is 100 micron size and you know your energy is going to decay by the 100th grain, then in those small particles, that's like a meter. But if you have meter-sized boulders, that's 100 meters or something. So made up numbers. But we'll reuse the same simulation methodology that we had before, but instead of dragging that velocity along the floor, I'm going to use a piston to initiate the wavefront. And so what's going to happen as that wave moves down the channel, the energy in the wavefront is going to decay. And so we're going to measure that by the collisional velocity in the wavefront, or this VM term. And so then we can build up the history at every radial position for different input velocities, which is what we did here on the right. So y-axis is that collisional velocity, and the x-axis is a distance normalized by particle number, our radius, and the colors are piston velocity. But just looking at any one of the trends, you can see like initially there's this larger collisional velocity that decays as you move along the channel. And so we'll use that equation that we came up with before to back out what this threshold velocity we need is, right? So I said like dilation, 40 centimeter depth for the cold spot. If we use that equation we had, that comes out to like a needed 4 meter a second or so velocity in the floor layer to sustain that surface dilating wave. And so we'll call that run out, the point where we drop below this line. And we can do this for a bunch of different material parameters. Specifically, we're thinking about velocity, maybe the thickness of the channel and the particle radius. So most of the results are on the next slide, and I'm going to probably skip over those real quick. But this is what I want to talk to you about. And I lost some grid lines here, but you can still see, so the range of from smallest to largest cold spot halos, you see the range that the surface grains are being modified there. And so in the pink pluses, I'm confirming for 4 different particle sizes, or 4 different sizes of particles in my channels, that we get this one-to-one trend with the run out distance with the particle number, right? It's just fixed on a particle number. So the pink plus on the far right is these meter scale boulders, and that is going to get me a distance of propagation where I think I could sustain this surface wave. That's within the cold spot range, right? But so those pink pluses are channels that I looked at that were too tall. So I mentioned there's that boulder layer that's like 10 meters thick, right? And so if I shrink my sim down to that size, is that red circle, so the distance the wave goes is not quite as far, but I can maybe do some scaling. So because of our simulation methodology, we're limited in the velocities that I can collide the particles at. So we're hitting them at like a kilometer per second, but if I scale it up to maybe lunar impact velocities, I get that black star, which is again within the range of cold spot scale distances. So what I'm saying is that even in this idealized granular case we're looking at, if you have this particle chain of meter scale boulders, you can transmit this energy over sufficient distances that I think you would get this kind of that wave I showed you before, making that dilation in the surface.
2 minutes.
Thank you. So yeah, great. So anyway, we did a bunch of fits, and this is how we got that scaling that I just used, but we're not going to talk about that. But so what I think is happening then is, so you have your initial wavefront is going to come off an impactor, and it's going to propagate outwards radially, right? And we're going to get out here, and in the regolith layer, that primary wavefront, it can't propagate very far. Like I said, like maybe a meter or something, because these grains are quite small here, right? And grains are good decimators of energy. But if you have this sublayer, this mega regolith layer with boulders where the impact energy is still decaying, that's going to continue over maybe these kilometer scale distances. And as long as the collisional velocity in the wavefront is sufficient enough, you're going to get this surface wave, which fluffs up the regolith. So I think this is a previously unconsidered impact process on any regolith covered body in the solar system. And so it could be used, you could look at the signature of a cold spot to maybe look at, buried objects or the local subsurface topography. But of course, this needs independent confirmation, other modeling efforts, maybe an experiment. And this is just a chain of grains, so more physically complete modeling as well. So that's what I got for you. I don't think there's time for questions, but that's it.